Hello everyone and welcome back. In this part, we will talk about relational schema design and normalizations. It will based on conceptual AI models to clean and normalize tables. So our goal is to move from high-level design to a practical table structure and make sure it's efficient. We will also learn to spot hidden problems like redundancy and update some issues. And you can see like what I'm going to talk about in general. So let's talk about mapping the tables, mapping the diagrams to tables. First of all, this is an example from the previous video. I am using it again here. We will have the entities, the customer and the order, which they will return, they will be the tables. We have the attributes, which will be the columns. And we will have relationships, one to many, which will be foreign key. For example, here, we have the customer and order ID, and customer ID goes to order ID as a foreign key. Also, when we use many-to-many relationships, we will need to have junction tables. And in this example, a customer places orders, and in the tables, we will have customer ID as a primary key, order ID as a primary key, and post customer ID will be foreign key, as you can see here. When we come to the functional dependency, it is the heart of the normalization. If knowing one column means you can find the other value of another, that's a functional dependency. It will tell us how information is related inside the table. And as you can see, we have an example here, which is the determinant and y is dependent. A relationship where one set of attributes uniquely determines another attribute. So first we will ask the question, the termination value got duplicated. If no, no further check is required. Function dependency is valid. But if it got duplicated, then we will need to ask another question, is values also duplicated? If yes, then it's okay. If no, then function dependency is not valid. To give an example, student ID. If we say student ID and student name are related, the student ID's functionality determines their name. We highlight that primary keys functionally determine all other attributes in a table by definition. So here, maybe there are two students called Emma Brown, but the ID will be the primary key and it will determine the difference. And we can ask ourselves why we need to normalize it. And let's imagine you have a one big spreadsheet with everything like orders, clients, items, and it looks convenient, like you can find what you need sometimes, but it's full of problems. Duplicate data wasted space and it's hard to update. Normalization will solve this problem. We will cover first, second, and third normal forms, and we will try to find solutions for these problems. The first normal form has it just removes repeating groups. Every field should hold just one value. If a customer has multiple orders, we should show them in separate rows or move them to another table. And we will have an example, but basically all columns contain atomic, indivisible values and no repeating groups or arrays in a single column. And to check the example of remove repeating groups, here we have unnormalized table, which has two customers, customer names, and phone numbers. The problem here is phone number columns hold multiple values. To fix that, we will use atomic values only. We will have customer 1, Alice Smith, but this time we will duplicate the row to show we have two different phone numbers, which will solve the problem that table had column that holds multiple values. In the second normal form, it kicks in when you have a composite primary key. It says every attribute must depend on the whole key, not just part of it. If not, we move it out. And to say in a table with composite primary key, no subset of key should determine any non-key attribute. This means eliminate partial dependencies. And this is only relevant if a table has composite key. To show an example how to eliminate partial dependency, we will have a table called enrollment, which has primary key student ID and course ID. The problem here is student name depends only on student ID, not the whole key. And so instead of having this, we can split into separate tables, which will have a student table, course table, and enrollment table, which is a junction table. Here, student ID 101 is Alice Smith, in the same example, but we don't need to know course ID to know student's name. And here, the course ID is database, and this is networks. And now we have a student ID and course ID junction table. Basically, every non-key attribute now depends on the whole composite key, not just part of it. In the third normal form, we remove hidden relationships. If A determines B and B determines C, that's transitive dependency. These should be split to keep data clean and modular. Basically, no transitive dependencies. If attribute A goes to attribute B and its primary key, we should separate into different tables. To show an example of eliminating transitive dependency, we have an orders table, which have order ID, customer ID, customer name, and order date. The customer name depends on the customer ID, not directly on the order ID. So customer name can be under the customer ID. So when we break this table to two, the orders table into two, we will have customer table and orders table. In the customer table, we will have customer ID and customer name. In the order table, we will have order ID, customer ID, and order data. So we don't need to have duplicate primary keys, and each non-key attribute depends only on the primary key, no indirect dependencies remaining. Normalization flow is a step-by-step cleanup. Start with the Macy data or raw data, fix repeating fields, first normal form, fix partial key dependencies for second normal form, then fix indirect relationships for third normal form. Basically, we are repeating groups, partial dependencies, and transitive dependencies. We are fixing it. And now I want to show you a practice example. I worked during a lesson. Actually, it is based on the example I had in the lesson. Here we have an unnormalized table, which has two products and couple variants. To make it a normal form, first normal form out of it, we are writing the product names and the variants small, medium, large for notebooks. And for marker, we have thick, normal, fine, and extra fine. As you can see, we don't have any primary key here because no single column uniquely defines each row. That's why we have a combination of both rows for primary key, which is product and variant. In the second example, we have another unnormalized table, which is client category, order, country code, and country. As you can see, when we make the first normal form out of it, we will have clients, which is repeating. We have client category, which can be corporate or individual. We have order numbers. This is special. The country code can be repeating, and country is the same as country code. And as you can see here, the primary key is the order because each order number is unique, so it serves as a natural key. When we come to the third example, we have a first normal form, as you can see, and we will translate it to the second normal form. And when we are looking at the attributes trying to see which one is the unique one, we can see for the customer table, we can have the mail address as the primary key because different customers might have the same name, but email address is unique for each. And that's why in the customer table, we have mail address as the primary key and last name and first name as other attributes. The second table is movie table. Again, we have a movie ID as a primary key. They're all unique. Title has only one ID. In the third one, we have ticket, which gets foreign key from the customer's mail address, and also gets a foreign key from the movie ID, from the movie as movie ID. And this one gets the primary key of mail address of the customer and movie ID of the movie, which makes each ticket unique. Every non-key attribute now marked on the whole primary key of its own table, satisfying to second normal flow. And we have eliminated the partial subsets of the original composite key. In this example, we have another first normal form, which has unique atomic values. And we will try to translate to the third normal form. So first we translate to the second normal form, then we translate to the third normal form. But I will just skip the step to make it second normal form and just go to third normal form. As you can see here, we have student number, name, state, postcode, faculty code, and faculty. And for the second normal, we will have faculty code and faculty. So when we look at these tables, student number is the primary key because it's the unique one. Name, state, postcode can be depending. Faculty code is also unique for the faculty, but it's a foreign key that comes from the faculty. The primary key, of course, is a number. And in the faculty attribute, faculty table, we have faculty code and faculty. And the primary key is, of course, faculty code. This goes to one-to-many from faculty code to faculty. When we, let's say, one student can enroll in one faculty, but many students can enroll in one faculty, and so on. And we have some questions here that we can answer together, more theoretical part. So let's say we have a second normal form table, and is the table already structured according to the first normal form? Yes, it is, because any table in second normal form must already fulfill first normal form, meaning atomic values and no repeating groups. Does the table meet those of the third normal form? Not really. Second normal form removes partial dependencies but not transitive dependencies, which means third normal form does have transitive dependencies, does not have, but second normal form doesn't guarantee third normal form. Are all attributes in this table required to store only one indivisible value, like list or sets? True. Atomicity is part of first normal form. Therefore, this table must have atomic attributes if it is already a second normal form. Can the primary key consist of more than one column in this table? Yes, because second normal form addresses primary keys. They are valid and often necessary in second normal form designs. Does each non-key column rely entirely on the full primary key and not just part of it? Yes. That's what's the point of the second normal form. No partial dependencies. Every non-key attribute depends on the whole primary key. And our non-key attributes only permitted to depend directly on the primary key, not on the other non-key columns. That's a rule for third normal form, which removes transit dependencies. Second normal form can allow them. So we don't need to have non-key columns. We don't need to have non-key column rely on the primary key. We can take a look at the second normal form again. We have customer, movie, ticket tables, and every non-key attribute now marked on the whole primary key and its own table, which satisfies the second normal form. You can see here. We have mail address primary key, movie ID primary key, and for the ticket we have mail address and movie ID. And if you ask the question, are non-key attributes, we talked about, can any row in table have missing value for its primary key? No, primary keys must not be null. If the primary key is made of single column, is the table automatically considered in the third normal form? Yes, no, a single column key avoids partial dependencies, but transitive dependencies may still exist, which doesn't mean it is third normal form. Is the use of auto-incremented or system-generated primary keys prohibited in this table? No. Storage keys like auto-incremented are allowed. Normalization is about attribute dependencies, not about whether keys are natural or artificial. It doesn't matter. We just have some rules for first, second, and third tables, and we need to have them in order to get what we need. Normalization is almost always the right answer for the exams, but in real systems, we sometimes denormalize for performance. That said, understanding normalization is critical for correct design. And bad design causes update headaches. Like when you change a department address in one row, you would better remember to change it everywhere, or you've got inconsistent data. That's why we use normalization. Like you can see, the pros is less redundancy and better integrity, but cons, we have to have more joins, and sometimes it can make things more complex. In summary, we have learned how to make a messy structure and turn into a clean logical schema using normalization. In the next part, we will look at how to implement this in SQL and bring the theory to life. And don't forget to understand and repeat these parts, I would suggest. Thank you for watching. See you in the next part.